In 1977, two spacecraft, Voyager 1 and 2, launched toward the unknown. Nearly 50 years later, they're still alive at the edge of interstellar space, whispering faint signals back to Earth. Their incredible longevity isn't due to solar panels or batteries. It comes from a small nuclear power source, plutonium-238. But now, scientists believe a new fuel, Americium, could reshape the future of deep space exploration, powering missions not for decades, but for centuries. Why do spacecraft even need nuclear power? Well, solar panels are great near Earth, but sunlight fades fast. At Jupiter, it's 25 times weaker. At Pluto, 1,000 times weaker. If Voyager had used solar power, its panels would have needed to be bigger than a football field. Instead, it carried a nuclear battery, called an RTG, about the size of a trash can. An RTG converts heat from radioactive decay into electricity. Inside is a fuel pellet, usually plutonium-238. As its atoms decay, they release a steady, reliable stream of heat, which is then turned into power. No moving parts, nothing to easily break. It just works. Voyager's RTGs started with 470 watts of power in 1977. Today, almost half a century later, they still deliver over 200 watts, just enough to keep vital instruments alive. Plutonium-238 became the gold standard for deep space. It powered missions to Jupiter, Saturn, and beyond. The Cassini spacecraft, which orbited Saturn for 13 years, couldn't have survived the cold darkness without it. The problem isn't performance, it's supply. Plutonium-238 has to be manufactured in special reactors, and production is extremely limited. We're talking just a few hundred grams per year, while a single mission might need 5 kilograms or more. This is where Americium comes in, specifically Americium-241. Its half-life is a staggering 432 years, 5 times longer than plutonium. But its biggest advantage, it forms naturally inside nuclear waste. Instead of building new reactors, we can literally extract it from existing waste recycling on a planetary scale. For Europe, this offers a path to deep space power that doesn't rely on the United States' limited plutonium supply. So what's the catch? Americium isn't as powerful. It produces 5 times less heat per gram, meaning an Americium RTG would need to be heavier to generate the same power. Plutonium is the high-performance option for missions with lots of instruments. Americium is the endurance option, perfect for small, low-power probes designed to drift between stars for centuries. Europe is already developing these systems, and NASA is considering it for a future interstellar probe that would travel for generations. To get around the power issue, engineers are looking at pairing Americium with super-efficient Stirling engines, which could boost power conversion from 5% to over 25%. This combination could truly transform space exploration. Plutonium took us to the edge of the solar system, but Americium, the long-burning, sustainable fuel, might just be what takes us to the stars. Thanks for watching. If you're fascinated by the future of space exploration, be sure to subscribe for more.